So, welcome everybody back. We continue this session now for the second talk again by a member of the Academy of Science of the Czech Republic, the Institute of Philosophy. Our new friend, Vít Punčochář, will be talking about the logic of assertability.
So first I would like to thank Joao for the opportunity to present here my work. It's a great pleasure for me. And in this talk I would like to present a non-standard semantic framework which I have been working on in connection with my dissertation. In my dissertation I'm trying to compare two different approaches to formal semantics. The first approach can be called ontic, and the second one can be called epistemic. And in an ontic semantics, the basic semantic concept is the concept of truth, and in epistemic semantics, the basic semantic concept is the concept of assertability. And I think that both these notions should be formally represented as relations, but the difference is that in the first case, truth should be represented as a relation between possible words and formulas, and assertability should be represented as a relation between information states and formulas. Something is true in a possible word, or something is assertable in an information state. And in this talk, I'm going to present a semantic framework of the second kind, epistemic framework. And the work is connected with the current work in the so-called inquisitive semantics. But the framework I'm going to present here is much more general than the standard semantic framework of inquisitive semantics. And in fact, it was intended as a generalization of inquisitive semantics. As regards the philosophical motivation, the work was inspired notably by Frank Feldman in his data semantics and Christopher Walker's conception of assertability in a context. But as you will see, the semantic framework is related to some standardly or extensively investigated topics as intuitionistic logic and its cryptic semantics and algebraic semantics. So cryptic semantics and algebraic semantics are the, I think, most common and popular frameworks as regards intuitionistic logic. So in cryptic semantics, we have some partially ordered sets as the basic semantic structures, and we have evaluation which assigns to every atomic formula an upward closed subset of the set. So we have this kind of structures here. And the semantic conditions introduce a relation between the element of the structure and formulas. So we have a relation here, and the semantic conditions look like this. In algebraic semantics, the basic semantic structures are algebras, and in the case of intuitionistic logic, Hating algebra, so we have semantic structure of this kind. evaluation which assigns to every atomic formula a point in this algebra. And the evaluation is extended in the natural way to every formula. So the typical semantic condition of this kind of semantics is I would like to present my framework as a viable alternative to these two frameworks. And in fact, it is a combination of these two frameworks, and it can be seen as something in between these two frameworks. It is a relational semantics. It is similar to cryptic semantics, but it is closer to algebraic semantics, as you will see. And I will introduce the semantics in two steps. In the first step, I will introduce a non-standard epistemic semantics for classical logic, classical propositional logic, which can be seen as a particular case of the general framework. And in the second step, I will introduce the general framework as a natural generalization of this particular case. So I will be working with the standard propositional language. We have atomic formulas and constant for contradiction or absurdity, and conjunction, disjunction, implication, and negation is defined in intuitionistic way. And the semantic is epistemic, so I need information states. It is quite common to model information states as sets of possible worlds. So this goes back to Robert Skolniker, and we can use this definition. And possible worlds can be seen as functions assigning truth values to atomic formulas. And now, we can introduce something like evaluation, and evaluation assigns to every atomic formula a set of information states in which the formula is asserted. And we can accept that an atomic formula is assertable in an information state if and only if it is true in every possible world in this state. So, according to this definition, if this is just the set of all possible worlds in which P is true, then the evaluation assigns the power set of this set. And the second step is the introduction of assertability relation between information states and formulas. So, contradiction is assertable in a state if and only if it is the empty state. An atomic formula is assertable in the state if A is in this set. Conjunction is assertable in the state if and only if both conjuncts are. Now the interesting case is the case of disjunction. Disjunction is assertable in a state A if and only if there are some states B and C such that first disjunction is assertable in B, the second disjunction is assertable in C, and B, the union of B and C is the state A. And last condition is for implication. Implication is assertable in a state if and only if the consequent is assertable in every substate of the state in which the antecedent is assertable. So we have a semantics, and we can ask what is the logic of determined by the semantics, and it is just classical logic. This is not very exciting, but I think that the semantic framework is interesting for several reasons. One of which is the untypical condition for disjunction. But I would like to stress another aspect of this semantics. It is a relational semantics. So we have a structure of information state, and we define a relation between the elements of the structure and formulas. But the structure is Boolean algebra of sets, so it is a structure normally used in algebraic semantics. So, in a sense, this framework combines algebraic semantics and relational semantics. And we can ask, so now I will generalize this framework, and to do that we can ask what is necessary from this framework, from the algebra of information state, to formulate the semantics. What do we need? And we need the zero element of this algebra. Here we need the join of two states, and we need this ordering. But the ordering can be defined in terms of the join. So, in fact, we need just the zero element and the join of the states. So, it seems to me that quite natural generalization can be based on this kind of structures. So, I will introduce this definition of an algebra of information states, and it is defined as a joint semi-lattice with zero element. So we have idempotence, commutativity, and associativity for the join, this condition for zero element, and ordering defined in the standard way. So it can be seen just as partially ordered set such that for every two states there is supreme of these states. So these are the algebras of information state, and I will need also the standard concept of ideal. An ideal is a downward closed subalgebra of these algebras, which can be defined as ideals will play a similar role as upward closed subsets in standard descent. So an information model is a pair, A and B. A is an algebra of information states, and B is evaluation. Defined as a function assigning an ideal to every atomic formula. And with respect to these information models, assertability relation can be defined as before. So we have the same conditions. Now we have the zero element of the algebra, and here we have class and the ordering of the algebra. And the natural question arises: what is the logic determined by this semantics? And I do not have a syntactic characterization of this logic, but it's evident that if it is defined in this way, it is an untypical logic which is not closed under uniform substitution. It seems very natural as you will see to introduce another condition, distributivity. So it's possible to define distributivity even though there is just one operation. An algebra of information states is distributive if and only the following condition holds. So whenever we have two states M and B, there is A plus B, and an element C, which is under A plus B, then there are two elements B and E, such that B is under A, E is under B, and the join of B and E is C. So this can be called distributivity, and there is a reason why this is called distributivity, because if we consider the algebra of ideals, we can take join several elements with zero element, and we consider all the ideals. They form a lattice, and this lattice is distributive if and only if the similarity is distributive in this sense. This is a known result, and if the similarity is distributive in this sense, if it is in fact a lattice, it is distributive in this sense if and only if it is distributive in the usual sense. So this is just a generalization of standard distributivity. This is a very natural condition in this framework. This is what, it can be shown that the logic of all distributive semi-lattices is Diffusionist logic. More surprisingly, if we ask what is the logic of all Boolean algebras, it is also Diffusionist logic. But the logic of all finite Boolean algebras is classical. Now I will show that distributivity is really necessary to get the intuitionistic logic. For this purpose, I will introduce two technical concepts. So ideals are defined by this condition A plus B is the ideal if and only if A is the ideal and B is and this condition can be split into two conditions. You can see this condition is defining some property of formulas. So the first condition is persistence. So we say that the formula is persistent if it holds for the formula that the inverse condition defines second property. A formula is regular with respect to some information model if this condition holds. So these are just some properties of formulas with respect to some information model, and we can define this as also as properties of the algebras of information states. So we say that an algebra of information states is persistent if every formula is persistent in every information model based on this object, and the same is regular. So now we can see it as properties of the algebras of information states. And the surprising result is that these two properties are equivalent. So an algebra of information states is persistent if and only it is regular, and they are equivalent to distributive. It is distributive. So just to show how it works, suppose you have an algebra which is not distributive, so I can have this typical example. Take evaluation which assigns to P this ideal, and which assigns to Q this ideal, generated by this element. Then we have P or Q here, but not here. So this junction does not preserve persistence. And similarly, implication does not preserve regularity. So here we have this ideal and Q this ideal. Then we have P implies Q here, P implies Q here, but not here. So we can define the notion of a proposition expressed by a formula is just a set of information states in which the formula is acceptable, and the previous result leads to the conclusion that if the algebra of information states is distributed, then propositions are ideals. And in fact, the algebra of proposition is the algebra of ideals. So now I would like to discuss the relation of this semantic framework to standard algebraic semantics, and the relation is quite strong. It is expressed in this result. So suppose you have a mating algebra. evaluation in this algebra in the sense of algebraic semantics. With respect to this evaluation, we can define the evaluation in my sense. So it is defined in this way. To every atomic formula, it assigns the ideal generated by the element assigned B by the evaluation B. So it will be defined in this way. And then this property is extended to every formula. So here we have the element assigned to a formula phi by standard algebraic semantics, and the proposition which we get from our semantics is the ideal generated by this point. So this is the relation to algebraic semantics. So in a sense, this semantics can be understood as a generalization of standard algebraic semantics. Because if we consider these special models, they just correspond in a way to algebraic models. And it can be, this result can be applied to the special case where when the algebra is the Lindenbaum algebra of a given logic. So this is just a straightforward consequence, and it shows that for any logic which is stronger than intuitionistic logic, the Lindenbaum algebra can be understood as a canonical model in our sense. So we have a logic L, and something is theorem of the logic L if and only if it is assertable at the top element of the Lindenbaum algebra of this logic. So this is a way how to construct canonical models in this framework. And another way is more, so it's possible to formulate another construction of canonical models which is closer to standard constructions in relational semantics, and it can be defined in this way. So suppose you have a super-intuitionistic logic L, so a logic which is stronger than intuitionistic logic or intuitionistic logic or historical logic, and we can define a canonical model in this way. So take an algebra of information space where the set S is the set of all theories of this logic, deductively called sets of formulas. The zero element is just the set of all formulas, and plus is just the intersection of those theories. And evaluation can be defined in a short way. Now it is necessary to show that this structure is distributive, and distributivity here means just that if we have two series, A and B, these are typical sets of formulas, and we have a series C which contains the intersection of A and B. Then there are some series and E. Such that D contains A, E contains B, and the intersection of D and E is just the theory C. And this holds for superintuitionistic logics. So in this sense, it is distributive, and that is the result which shows that it works like a canonical model construction in the standard way, but I would like to stress that the canonical models are different structures than the standard canonical models of superintuitionistic logic. Now it's possible to extend this framework to modal logics. You can enrich the algebra of information state by an additional operator G, for which we require these two conditions. And this enriched structure can be called modal algebra of information states, and we can add this semantic condition for box modality. So box phi is assertable in A if and only if phi is assertable in A. Then this works perfectly for normal, like a normal modality topology K. So if we take, for example, calculus for intuitionistic logic and add two rules for the K modality, we receive that logic which is complete with respect to the semantics. And to prove the completeness, we can use the canonical model construction, as was described before. We just have to define the operation G. It can be defined in this way, and the two rules for the K modality guarantee that this is deductively closed set of formulas. So it is an operation of the series of logic. So and it works. As before. So this kind of construction can be used quite generally. It can be used, for example, for any normal model logic, for any superintuitionistic model logic of this kind. What is interesting that the relation between this kind of semantics and algebraic semantics is less straightforward now if the box operator is present. So to describe the relation to the algebraic semantics, I mean the concept of a residual of an operator. So if we have an ordered set and we have two monotone functions on this set, f and g, we can say that f is the residual of g if the following conditions hold. So ga is under b if and only if a is under fb. And we can call the pair of functions as the pair of residuated pair of functions. And the relation to algebraic semantics is now expressed in this result. So consider we have anything algebra. And this an additional operator f. The operator satisfies these two conditions. So these are the structure which are used in the algebraic semantics of super-intuitionistic logics. We can take now a different structure, similar but not exactly the same. We have S plus from this structure, the zero element from this structure, but another operator, G. And if we suppose that this is the residual of this operator, then the nice relation works as before. So if you have any questions, you can ask. Is it clear so far? Okay, so how much time do I have?
20 minutes.
20?
Yes.
So the interesting thing is the role of disjunction in the semantics. We can naturally ask the question what happens if we introduce the standard semantic condition for disjunction. So we can introduce another operator with the standard condition for disjunction, and it turns out that this kind of operator generates non-regular propositions, because if we have algebra of information states and we have an ideal which expresses which is the proposition expressed by formula phi, and another ideal which is a proposition expressed by a formula psi. So then, if we ask what is the proposition expressed by phi or psi, it's just the union of these two ideals, and it does not have to be an ideal. So, if we ask, for example, what is the logic of distributive algebras of information states with this extended language, it will definitely be a logic which is not closed under uniform substitution. But still the logic can be described in a relatively elegant way. So I have here a complete system of natural deduction. This is the Buddhist semantics, so it consists of two groups of rules. So, but maybe I was too intense. But it seems to me that this is one important advantage of the semantic framework, that it enables us to distinguish between these two kinds of disjunction, and I think this has this has some applications in natural language, so I will try to illustrate this with the following example. So consider this example, which I took from Stonemaker. So suppose we have an air raid during the Second World War, and someone is reasoning in the following way. Either I will be killed in this raid, or I will not be killed. Suppose that I will, then even if I take precautions, I will be killed. So any precautions I take will be ineffective. But suppose I'm not going to be killed. Then I won't be killed even if I neglect all precautions. So on this assumption, no precautions are necessary to avoid being killed. Anyway, any precautions I take will be either ineffective or unnecessary, and so forth. So this is a nice argument. It is a little bit wrong, but it is difficult to identify what is the problem here, and it seems to be a sound argument, because if we try to formalize it, we got something like this. So we have P or not P from the hypothetical assumption that P we can infer Q. From the hypothetical assumption that not P we can infer R, and from this we can infer Q or R. But it seems to me that this is a wrong formalization, that the right formalization is this one, that the disjunction at the end is what I call sometimes intentional disjunction, which works in a different way than the disjunction in the premise. So I will be killed or I will not be killed is extensional disjunction in a sense, and taking precautions will be either ineffective or unnecessary. This intentional disjunction which is related to the whole information state. So just to illustrate this picture, so suppose this is an information state. There are just possible worlds. Here is a substate consisting of worlds in which I will be killed. Here is a substate. There are possible worlds in which I won't be killed, and we have the union of these two states, and it guarantees that it is assertable with respect to the whole information state that I will be killed or I will not be killed. But here, with respect to this part in which I will be killed, it is assertable that any precautions I take will be ineffective because I will be killed in every possible way. Here, with respect to this part, it is assertable that the precautions are unnecessary, but it does not mean that with respect to the whole, to the union, it is assertable that taking special precautions would be either ineffective or unnecessary. So this is first example, and second example, also discussed in the literature as minus paradox. So suppose that 10 miners are trapped either in shaft A or in shaft B, but we do not know which one. Waters, that means to flood the shaft. We only have enough sandbags to block one shaft, but not both. If one shaft is blocked, all the water will go into the other shaft, killing every miner inside. If we block neither shaft, both will be partially flooded, killing only one miner. So here again, it seems that we have paradox because we have some premises. If the miners are in shaft A A, we ought to block shift A. It seems reasonable. If the minors are in shift B, we ought to block shift B. Either the minors are in shift A or they are in shift B. And from this, we should be able to infer either we ought to block shift A or we ought to block shift B, but this is problematic in a sense. So again, I think a possible solution to this paradox is that the problem is if we formalize the argument in this way. Here is just the box which can be interpreted in the only way. But the right formalization would be this, which is not a valid argument. So maybe it's reasonable to stop here. So thank you for your attention. Very much.